recording it. All right. So one of the things we will have to do today, and throughout Chapter 10, as it relates to these different things we're going to be studying, there's an algebra technique known as completing the square that we need to be able to do. So, does anybody remember anything about completing the square in a problem like this?
You have to have numbers.
Don't you have to add something to both sides?
Yes. Now, you can add it to both sides, or you can add it to you can add and subtract it to one side. Either way works. Depends on the situation. Sometimes you complete the square in a problem that's not an equation. Actually, that's what's going to happen today. It's not an equation, so we don't have two sides. We just are taking an expression. For example, it's a lot like this. If I have the expression 7, and I want to change the way it looks, but I don't want to change its value, I could add 3 to it and then subtract 3, right? 7 plus 3 take away 3 looks different than 7, but it's the same as 7, correct? Right? By adding 3 and taking away 3. So this expression looks different than just a plain old 7, but those two have exactly the same value. Okay, and then what Addie's talking about is if I had the equation that said 6 equals 6, right? Those two sides are balanced. If I add 3 to this side, to keep them balanced, I have to do what? I have to add 3 to this side, right? And so it's kind of two different concepts, but closely related, okay? So yes, that is one part of it, okay? What's another part that you remember about completing the square? Anything? Well, I'll give you this hint. This is what we're after, something like this. When we say completing the square, we're trying to make a quadratic, a trinomial, into what we call a perfect square. That means something that is square. And so this particular one would be x squared plus 12x plus 36. This is what we call a perfect square trinomial. And it is a perfect square trinomial because it can be factored into two binomials that are the same. So it can be factored into, so x squared plus 12x plus 36 can be factored into the quantity x plus 6 squared. So what is it about x squared plus 12x plus 36 that we know factors into that? Does that help jar your memory at all? What is it about? I mean, so what are some connections with those numbers? You got a 6 on the factored version, you got a 6 in there. On the trinomial version, you have a 12x on the middle term. You have a 36 on the last term. Well, they're related to 6 in some way, right? The 36 is what? 6 squared, right? That last term is always, the first term is always this one squared, and the last one is always this one squared, right? And then the middle term is always what? I mean, if you go back to FOIL, you got the first, you got the last, and what's in between? Outers and inners, right? The outers and inners added up. Well, that would be x times 6, and 6 times x, that'd be 6x, and 6x adds to 12. So is it a coincidence that this number here is double that number in there? It's not a coincidence at all, right? Because it's twice the inner product, right? 6x plus 6x makes 12x. So this number in the middle has to be double what these two would be right here, okay? And then the last number is that one squared. Now, the other thing that has to happen for this to work is you have to have a 1 in front of here. Okay, so if there's not a 1 in front of there, you got to factor that out like in these problems, okay? So, let's go through the first one here. So just in your notes, we'll just go through one together here. So the idea would be to turn this one into a perfect square, this first one, x squared plus 4x minus 32. So write that down, x squared plus 4x minus 32. So the idea would be and then it said equals 0 on the other end. So the idea would be to, I'm going to put the minus 32 way over here. Maybe I did that. No, I didn't. Okay, so I got x squared plus 4x minus 32. So what I want to do is just take those first two terms, okay, and then the c term, the constant term, I just kind of scoot it off the side and leave myself a little bit of room. And this is what relates to what Addie was talking about. So what we want to do is we want to look at this number right here, and we want to say, well, that number's double, right? Remember in the last example I gave you, that was the 12, but when I had it in factored form, it was a 6. It was half of that. So we always want to take half of this number here, and then we want to square that, because that's what we want our third number to be. So remember the one we just had up there, we had the 12x, and then the last number was 36. So if we take half of 12, that's 6, and then we square that, that's 36, and that's what our last number should be. So half of 4 is 2, and then squared is 4. Now, I can't just add a 4 on there without changing the problem, right? And so this is where Addie was saying, don't you add something to both sides? So yes, I could add a 4 now over to the other side. That would be fine. But in the you're going to see in the problems that we're doing, or sometimes in the problems we're doing, there isn't an equals anything. We're just trying to rewrite it. So you could just take away 4. You could do that. Now, so you can do either way, because if you look at what's going to happen, what am I going to do? I could add these over to the other side. That would be fine, right? And then you have a plus 4 over there. So to keep it balanced, I could have added a 4 on the left and added a 4 on the right. That would have kept everything balanced. Or I can just add a 4 and take away a 4. And that has the effect of basically not doing anything, right? It has the effect of adding a 0, okay? But now what I can do, though, is I can just group these 3, right? So I can just group these 3 right here. And that makes that factored, like so. So I end up with x squared plus 4x plus 4. Now again, some people would have said, some teachers may have just added the 32 over to the other side right away. Okay, and then done what Addie suggested, added the 4 on the left and added the 4 on the right, and then you get a 36 over there on the right, which I'm going to get here in a minute. Okay, all right, does that make sense? So what you get in here is always this number, whatever you got when you add half that number, that's what's going to go in there. Okay, and then we can add the 36 to the other side. Okay, this is what you learned in algebra class before you, well, I don't know about before you did quadratic formula, but about the same time you were learning factoring, you were learning quadratic formula. This is another way to solve quadratic equations. Get a perfect square, so that way you can square root both sides. See, because the problem with the original thing, we can't get the x by itself on this. We can't get the x by itself, and this doesn't factor. We could, well, this one actually might factor. This one actually does factor. Okay, but maybe it didn't factor, right? So what we can do is we can do this completing the square business. So we do the square root of both sides. Now don't forget, square root of 36 is plus or minus 6. Okay, and then we get, then we subtract 2 from both sides. So we get negative 2 plus 6, which would be 4, or we get negative 2 minus 6, which would be negative 8. Okay, there's our 2 answers. Now again, this one does factor. This would be x plus 8, x plus 4, or excuse me, minus 4. Equals 0. So sure enough, negative 8 and 4. So factoring's nicer and quicker, and it just shows us, hey, we got the same thing. Of course, quadratic formula would work too. Matter of fact, where's the quadratic formula come from? We're not going to do it today. Miss Andreessi did, I bet. You just complete the square on the basic generic quadratic. You just take this and you complete the square on it like we did. And that's where the quadratic formula comes from. Okay? All right, so this idea of completing the square is important. So let's go to this next one. Okay, I'll help you get started here. What's different about this one is you have a 2 in front. Okay, so what we have to do is take out the 2. We'll go ahead and use decimals here, we'll be fine. So we're going to take out a 2, which would make that a 2.5. You might be saying you can't take out a 2. Well, we have to take out a 2. You can't take out a 2 and leave them whole numbers, but you can take out a 2, okay? And that becomes 2.5 equals 0, okay? All right, so now we've got that. So now on that inside the parentheses, what was the process? What did we just say we wanted to do? What did we start right here? We looked at this number and did what? Divided by 2, half of it, and then what? Squared it. So take that b term, the middle term of your trinomial, the x term, if you will. Take the x term, divide the coefficient by 2, and then square it. Okay? So we're going to take 2.5, we're going to divide it by 2. Now so now look, I'm going to write a little smaller in here because I got to squeeze some stuff into here. So I got x squared plus 2.5x, and then what did we get? 1.5625. Now, shoot, I never did this. Now, here's why, this is why I kind of comment when Addie said you can add to both sides, because when you get one like this where you pull the 2 out, you don't want to just add to both sides. That actually will get you in a little bit of trouble. So what I want to do right here is I just added a 1.5625 into this problem. What do I need to balance that? Subtract the 1.5625. And here's why I can't just add that over to the other side, because I didn't really add a 1.5625 to this problem. I actually added a 2 times 1.5625 on this side, right? Because that 2, it's sitting inside the parentheses, there's a 2 on the outside. So I'd rather do this, and then what do I have to not forget to put in? I got to have the -4 in there too. The -4 is still in there. So it's just like I took that -4 and just shoved it out of the way, because I don't think it's what I want. I knew that's not what I want. So I shoved that -4 out of the way. It's got to stay there, but I shoved it out of the way. And I said, what I'd rather have in that third slot is a 1.5625. Then I got to take it away so I keep things balanced. And then I've got this. Okay, so now I've got 2. Okay, so now this part, so I'm going to do my 2 times, I'm going to group these 3 here, and then I'm going to group those 2 there, right? So this is going to be 2 times the quantity of, what's this going to be in here? X plus, and honestly, we're not going to have, most of them are not going to get this messy with decimals, but this would be, what would be right here? This is probably the part that's easy to mess up here. So once we get this into our factored version here, I'm just looking at those 3. What's going to be right here? What do we have on this one? What went right there? 2, right? The thing we got when we took half of this, right? When we take this number, divide by 2, and then we square that, right? That's the number, the thing we got when we divided by 2. The first of those 2 steps is what goes in there. So what's going to go in this one? 1.25. And that makes sense, because when you square these, when you do your FOIL to this, this will be 1.25 squared, and that's where that number came from right there. Okay, now, what else do we have here? We have minus, we can't forget the 2. What are these 2 numbers now put together? Those 2 there. 5. I already took the negative out here, so it'll be positive. 5 point, maybe I should have kept that a plus. But 5.5625 equals 0. Okay, now I'm not going to finish it out solving it, because I don't really care about the solving part. It's the difference, or it's the completing the square I care about. So, okay, so when I had to take out that 2 and I completed the square, that 2 is still a part of all of those terms in there. So the 2 will connect with this, and then the 2 will also connect with that. It's like distributing. I'm distributing the 2 to this group of 3, and I'm distributing the 2 to that group over there. Okay? And so that's why I couldn't just add that onto that side. Let's try one more like that. Let's do this last one here. Number 3 says 9x squared minus 12x equals 14. Now, if the 14's already over there, I'm just going to leave it over there. That's fine. Okay? But I have to take out a what here? Well, I could take out a 3, but what do I have to take out? 9. I have to take out a 9, because this completing the square only works if the 1 is in front of the x squared. Okay? So I got to take out 9. Now here, since I'm going to get a repeating decimal and stuff like that, that's, let's see, do I get a repeating decimal? Yeah, now I better leave it as a fraction. I better leave it as a fraction. So, and that'll actually be a little less messy than that way. So I'm going to look, so what's 12 divided by 9? 4/3, right? So that'll be 4/3 x. Now I'm going to leave myself some space in those parentheses, and then I still got that 14 over here, right? Okay, so what do I have to do? I have to take half of this number, right? Now remember, the way we got this 4/3, if you're not sure on this 4/3, remember, when you factor out something, what you're doing is dividing, right? When you take out a 9, you're dividing this by 9. 9 divided by 9 is 1. When you take out a 9 from a 12, it's 12 divided by 9. That's how we got it. 12 divided by 9, right? That's where the 4/3 came from. What's half of 4/3? 2/3, right? Half of 4/3 is 2/3. And then you got to square it. 4 9s. But we got to take away a 4 9s, right? So I'd rather do that than the thing about adding it to the other side, because that gets you in trouble whenever you have a number that you factored out like this. Okay? All right. So I'm just going to do that. So I'm going to take these 3 and group those. So I'm going to have a 9, and then that's going to be what? X. Just looking at these 3. It has to be a minus anytime. Now remember, this last term's always positive. This last term's always positive. So minus 2/3. Remember, this number is what we got when we took half of that. And then that's squared. And then I've also got this minus, and I have the 9 and the 4 9s, right? Now I took the minus as was there. And then I got equals the 14. Okay, so I just got to remember to keep, I'm looking for this trinomial. That's the key. I'm creating this trinomial that I can do a perfect square. That's the idea. Okay? And so I get this, and then that would just, those would cancel just before I could add that over. I mean, if I was going to finish this, I'm not going to finish right now because that's not the part I really care about. Minus 4 we add over, there's 18. We could divide, do the square root, and on and on. Okay? So that is completing the square. All right, so that's going to come up here in a little while later with what we want to do. All right, so why do I have this wooden cone up here? Because what we are going to be looking at is conic, something called conic section. Now there's a page in your book, you don't have to look at that right now. I'm going to show it to you here in a minute. Conic, from the word cone, conic sections, okay? Now, there is the 4 main, what we call conic sections, shapes that are created from a cone. And we have 4 of them here in this cone here. There's a circle, there's an ellipse, there's a parabola, there's a hyperbola. And then there's what we call the degenerate cases, the trivial cases, the cases where it creates a point, a line, or 2 intersecting lines, but they're also considered part of what we call conic sections. Now we're going to be studying this over the course of the next multiple weeks, okay? Today is just going to be about circles, okay? And then next week, parabolas for a couple days, because you already know some about parabolas, okay? And so we'll be doing some about with those, all right? So if we take a look at what would be on page 733 in your book, and I'll show you in a minute, it's going to show you some pictures like this. Well, when we call them conic sections, this word section means we're going to slice. If we take slices through the cone, it creates these different sections. So it's kind of cool how these different shapes can all come from this one three-dimensional object. So the first one is if you slice a cone so that it's perpendicular, call this the axis of the cone up and down here, vertically, then if you slice perpendicular to that, you're going to create a circle, right? And obviously get bigger as you go down the cone, right? So that's one of the conic sections. If you slice at an angle other than 90 degrees to the axis being the metal rod you see going down here, if you slice at an angle different than that, you get an ellipse, okay? Which is related to a circle, right? But it's oval, an oval shape. If you slice parallel to the axis, okay, you get this shape, which looks kind of like a parabola, but it's not. It's actually a hyperbola. It's actually one branch of a hyperbola, and I'll show you the cones. It's conic sections are typically created with two cones, point to point. I'll show you that in a minute. So that's if you're parallel to the axis. And if you slice at an angle other than parallel to the axis, like so, but it doesn't go all the way through the cone, it goes down to the bottom, that's when you get your parabola. And that would be the parabola. Okay? And so that's why they're called conic sections. Okay? So in your book, there is, you have this picture, which we'll see later on. So again, the four that I just showed you, so perpendicular to the axis, and this is a cone on top of a cone, okay, or a double cone, or it's called a lot of different things. But that's going to create a circle or down here. Now, if you'd happen to go right through the vertex, if you would go perpendicular to the axis and slice right through the vertex where the two cones meet, that's when you get a point, right? Geometry, day one of geometry, what do you learn about? Points, lines, and planes, right? Points, lines, and planes, the first three undefined terms you learn about geometry. Well, this is, when we talk about slicing the cone, we're slicing with a plane, right? And so this is all related to geometry this way. Okay, so you take and you go at a little different angle like this, but you go all the way through the cone, you go through both sides of the cone, you create the ellipse. Now, if you slice at an angle other than perpendicular or parallel, and you just go through the top or the bottom of the cone, and then one of the sides, is where you get the parabola. Now, if you would take that plane and you would slide it so that it just actually touched on the outside of the cone like that, that's when you would get a line. The intersection of the plane and the cone would be a line. So again, that's just a very specific example, and so we don't mess with those very much. And then this is where we talked about hyperbola. A hyperbola actually looks like two parabolas back to back. Now they're a little different shape than a parabola, so they're not parabolas, but that's called a hyperbola, and that's when you slice parallel to the axis. Now, if you happen to go right through the vertex of the cone, right through the middle of it, right here, right through the axis, then you would create these two lines. Okay? And so that's where those 7 different shapes come from. Okay? All right, so we're just going to focus on, for the most part here, the idea of a circle here. So, this is in your book too, but I thought this was important, so I put it up here. We could begin by defining conics in terms of intersection of planes and cones like we just did. So we just showed them. We didn't define them that way, but we just showed them. We could also define them algebraically, and we're going to talk about that. This is what's interesting. Every one of those shapes can be created by an equation of this form right here. So that's another kind of cool connection to our algebraic stuff that we have. Squareds is the highest power, and those are all the different combinations of x and y. You can have an x squared, you can have a y squared, you can have just an x term, just a y term, you can have a constant term, and you can have a combined xy term. Okay? Now you can't have a combined xy squared or something like that, but any of this shape. Now, obviously a line, if you let a, b, and c all be 0, now you got a line. Okay, now you got a line. Okay, but if you change these values of a and b and so forth, you get all these different shapes. So I wanted to show you that real quick. But what we're going to do is we're going to look at them. We're going to define these in their geometric properties, which we'll get to here in a second. Okay, but first I think this is pretty interesting, so I'm going to show you this. So right here we got our equation. Now right now the a is a 1 and the c is a 1. And then we've got this over here. So right now what we have is we have the equation x squared plus y squared minus 1 equals 0, which would be x squared plus y squared equals 1. That's the equation we have right now. Okay? If I change any of those things, okay, and I can change it by sliding right over here. Okay? Let's say I change the f value right here. There's your point. All that's doing is changing what?
How big it is.
How big it is. What's it changing in the circle? The what? The radius. That's just changing the radius. So obviously this number right here is related to the radius of the circle. Okay? So let's just, so I change that. Okay? Now, let's change the D and the E. The numbers on just those terms. Let's change just the D first. That's the number on the x term. Watch what happens. Still a circle, isn't it? Doesn't change the shape, just changes how big it is and changes what else? Changes, no, yeah, that's how big it is. Changes the radius, but what else? Its location. And it only changes location in what direction?
Left or right?
Horizontal, on the x, right? Makes sense. We change the number that's part of the x, it changes its location on the x. Now, what do you suppose is going to happen when we change the e? We're going to see that thing move up and down. And change size as well. All right? So we got a lot of different changes going there. All right. We notice we didn't change the b at all, right? And we didn't change the a or the c. But now, what happens if I change the a or the c? Instead of a 1x squared to 1y squared, let's say I just change the a value. Okay? Let's just change the a value. What's happening? It's becoming what shape? An ellipse. It's an oval. It's turned from a circle into an oval, and what shrunk? In the horizontal direction. Notice I changed the number on here, made it bigger, and actually squeezed it this way. That makes sense. Remember when we were talking about translations, we were talking about compressing graphs? We said when you went horizontally, it was like the opposite of what you thought. And so when we made that number bigger, it actually went that way. Okay? And then what about if I change the C? What do you suppose is going to happen? It's going to change that one. Right? And it's now, well, okay, now what happens when I go negative?
It's split.
What shape is that? That's the hyperbola. Okay? So all of these, just from this equation, right? All these different changes in these numbers. And then what does the b do? That's the one we're not going to work with very much. Possibly not at all. But when you change b, it rotates, right? It's and if you go too far, switches into a hyperbola. Okay, so it's kind of cool. All right, how this from this one equation, we just change those coefficients on there. It makes all these different shapes, which happen to be the different shapes you can create by slicing and cone. All right, so that's just kind of an introduction to what we're going to do, kind of the big picture thing. Let's talk just about the equation of a circle first of all. So, you'll get to that in your notes here in a second. So this is what we mean by a locus of points. So I want you to write this down. I want you to write this down right here. A circle is a locus of points, so that thing in the blue. Okay? Because every one of these, we're going to have a definition. All right, now you probably wrote this down in geometry. I don't know if you did circles in geometry. Probably depends what geometry teacher you had. But I think most of them do it. A locus is just a set of points. But we use the term locus because we put it on a XY coordinate system and it has a location. The points have a location, right? That's kind of where that term comes from. But a circle is a locus of points, or you could say a set of points in a plane that are a fixed distance, which is the radius, from a fixed point, which we call the center. Okay? And so this is called collecting seeing the locus of points. And so you can see as it drags the trace around there, that's what creates a circle. Those are all the points that are r units away from a fixed point, which is the center. Okay? And so that's our circle right there. Now, how do we get the equation of the circle? Okay? Well, that's what we're going to go through here real quickly. And that is simply this. Here's my circle. So if you want to draw this picture right here. And it is simply the distance formula. It is simply the distance formula. And the distance formula is nothing more than the Pythagorean theorem. Okay? The distance formula is nothing more than the Pythagorean theorem. Okay? Because this is a x value of h. This is an x value of x right here. So this distance right here is x minus h. This right here is a y value of k. This right here is a y value of y. So this distance right here is simply, well, I'm going to put y minus k because it doesn't matter, you're right, it could be k minus y, but that would just make it negative. We want the distance to be positive. So I'm going to do y minus k. It's just because this point's below that point, doesn't matter. We're going to square it anyway, so it doesn't matter if it's negative or positive. So what is r going to be? It's going to be this squared plus this squared, and then the square root of that. Okay? So distance, right? And that's what the distance formula is. The distance formula is just subtract the x's. So I did x minus h, subtract the y's, y minus k, and you square those, and then you do the square root. Okay, this is Pythagorean theorem. That's what it is. Pythagorean theorem. Okay, so that's what r is. Now, if I square both sides, we get this, right? I go ahead and square both sides, which actually is what, if you just left it as Pythagorean theorem, you know, that's what you would have had, right? The distance formula is so we can just figure out what r is, okay? And but that is called the standard form of the equation of a circle, okay? Well, maybe if you're thinking about what we did earlier in the period, when we were completing the square, you can kind of see why we might be interested in completing the square. Look what you have in here. You got x minus h, you got x minus something quantity squared. That's what we were doing when we were completing the square. Why is that important? Because what is this number right here, this h? No, in our circle. It's the x coordinate of
The point of
what part of the circle?
the
The h over there. It's the x coordinate of the middle, the center of the circle. What's k? The y coordinate of the center of the circle. So this number here combined with this number here gives you the location of the center of the circle. And this number over here is the radius of the circle. If you know those two things, you can draw any circle you want. If you know where the center is, and if you know what the radius is, you can draw the circle, right? If you know what the center is, and you know what the radius is, you can draw the circle, okay? And that's it. But it just comes from the definition of a circle, which is a set of all points equidistant from a given point. And then we just label them, and there we go. This is called analytic geometry. A lot of times in pre-calc books, it will say precalculus with analytic geometry or something to those terms. And even calculus books will say that, analytic geometry. Analytic geometry is just a combination of algebra and geometry. So we're taking geometric shapes and we're putting them on an XY axis and using algebraic equations to describe them, okay? All right, so what are some problems that we might be doing? Now, I'm going to give you, how much you get to use these on your quizzes is yet to be determined. Probably depends on what the quiz is over. If the quiz is over a couple of things, I probably won't let you use them, or I may not. If it's over all of them, then I may let you do it. But the gold sheet here was just a formula sheet. It's just a formula sheet with all the various ones we're going to be learning. Okay? So right now, the distance formula, I threw the midpoint formula on there because we're going to need that in a minute. And then you've got your circle equation formula right there. Okay? So you'll have these to look at, and you'll get comfortable with them, and you won't need them over time. Okay? All right, so let's take this problem right here, number 1. Okay? So write out that equation. So one type of problem you might be given. Now remember, we called this standard form. Standard form. Okay? So the standard form equation of this circle is right here. All right, well, the easiest question that I would ask would be, what is the center and what is the radius of this circle? What is the center and what is the radius? Well, I gave you the answer to that, right? Everybody see why that is what they are? Now remember, the standard form had minus signs in it. It was x minus h and it was y minus k, right? So this is your h right here is 2. And then this would be like having y minus a negative 5, right? Y minus a negative 5 is what we would have in here, right? So your k would be negative 5. So the center is 2, negative 5. And the radius, remember, this was r squared over here. So the radius is the square root of that side over there, which of course would be 3. So that's easy. And now drawing that should be really easy, right? We would come over here, we'd go 2, we'd go way down. You know, if I had you draw it, go way down here, and then you'd go up 3, and you'd go over 3, and you'd go over 3, and you'd go down 3, and there's your circle, right? I mean, if we had to draw, which we will, we'll have some problems where we would draw. But once you have the center, once you have the radius, piece of cake. Okay? All right, now, another question I could ask then on this same problem is, write the equation in general form. Well, general form is this right here. This is the general form. Okay? All right, so write this in general form would just be FOIL this out. So x squared minus 4x plus 4. So let's review that real quick here. So remember what, now you could write it out, you could write x minus 2 if you want, and do FOIL. It's simply this one squared. It's twice the inner product. When I say the inner product, it would be negative 2 times x and double it. So that'd be negative 4x. And then it's the last one squared. So negative 2 squared is 4. Remember that last one's always positive. Okay? And then this one would be y squared plus y squared plus 10y plus 25. Okay? So we would have that. So we would expand that one out. We would expand that one out. And now we want to get it in that general form, which remember the general form had a 0 at the end. So we want to keep all the terms on the left side. So we're going to bring the 9 over. This 4 and this 25 can combine with that when we bring that over. Okay? We want to write it in order. Notice how the order was on the other one. It had the x squared first, then it had the y squared. If there was an xy term, that would go in between there, but there isn't one usually. So x squared plus y squared, then the minus 4x, then the 10y, and then 4 and 25 is 29, and you subtract the 9 over, you get 20 equals 0. That's the general form. Okay? So obviously you know where we're going to go from there. We're going to do the reverse of that, right? We're going to have, here's the general form, let's write the standard form. Now, and it's fun enough just on its own because you get to complete the square, right? So that's a lot of fun anyway. But more importantly, we want it in the standard form because that tells us what? The center and the radius, right? And that's what you're going to see on that gold sheet. The reason we're writing these equations in these kind of goofy formats is because if we write them that way, they will tell us good information about the graph. Okay? And we can graph it and we can do stuff with it. Okay? So, here we go. What do we want to do? We're going to want to group these terms. Now, this time, since I had an equals, I went ahead and took Andy's advice and I went ahead and moved that 8 over to the other side. Okay? Because I know when I go to standard form, that's where I'm going to want to do it. So I went ahead and moved that 8 over. I knew I didn't want that. I'm going to put in my own constant term, the one I want to give me the completed square. So what do? I grab my x squared, my negative 4x, and then I leave myself a space to put in the number I want there. And then I'll take my y squared, my minus 6y, and leave myself a space. And then on the other side, I know I'm going to have to add those over there. Right? I could minus them like I was doing earlier, but in this problem it seems to just make sense maybe to put them over there. And so I'm going to add those over there to balance. Okay? All right. So what number goes here? You look at this number and do what? Half and square it. So half of that is negative 2, square it is 4, and then I got to stick a 4 over there. What about this one? 9. I got half that is 3, square it, well, negative 3, but it doesn't matter, I'm going to square it. So negative 3 squared, 9, put my 9 over there. Okay? So, what does that give me? Well, these 3 would be what? X what?
Plus,
Minus.
Minus 2 squared. This one,
X minus 3.
y minus 3. Remember, whatever you got when you had half of this one, or you can do the square root of this last one, whatever works for you, but that turns it into that. So these two are the same thing. All three of these lines are the same. They're just rewritten. But the way we write them can be useful. And again, this is a calculus thing. I tell my calculus students all the time, is the calculus will be way easier if we use algebra to put it in a look that is beneficial, okay? So, what is the center?
2, 3.
2, 3. Remember, because the equation form is minus h and minus k. So h and k would be the 2 and the 3. So it's like opposite of what they are, right? What's the radius? Square root of 5. We'll just write it like that. Remember the radius, remember this number over here is r squared. R squared. So r, the radius, would be square root of 5. Okay? And so that would be a question that might be asked. Here's a general form, write in standard form and name the center of the radius. Or maybe it's just here this is graphing. Right? I mean, just here's an equation graphing. Well, to graph it, you need the information you get from standard form, and that's why you would go to standard form. Okay? All right. Let's try this one. Okay, just trying to give you some different looks of how you might have to manipulate this equation and so forth. So write the equation of a circle with diameter endpoints at 4, -1 and -6, 7. Now I have some graph paper over here if you want to do your homework on it. I don't know that there's a ton of graphing ones, but every once in a while it could be good. And you don't need graph paper for this, really. It's just up to you. But if I was going to do this, I would plot these points. I think that's the first thing I would do. Right? I would go plot these points. I think I have it. I don't know if I have that grid on here or not. Yeah, looks like I do. Okay. Well, we know that the equation of a circle is this, right? It didn't say standard form or general form, so if it doesn't say, just you do whatever you think's easiest. Okay? So really all we need is h and k and r, right? We need the center. Well, how are you going to figure out the center? It's the middle of those, right? That's a diameter. That's where that midpoint formula comes in. Okay, I put it on there as a reminder. Remember the way to do a midpoint. The way to do a midpoint, now it looks like it's about right there, but I don't know if my graphing is that accurate. The way to do a midpoint is you add the x's and divide by 2. It's like an average. So we're just going to take 4 plus -6 and divide by 2. And then we're going to take the y's, -1 plus 7 and divide by 2. So it's just add the x's, divide by 2, add the y's, divide by 2. That's the midpoint. So 4 plus -6 is -2, divided by 2 is -1. -1 plus 7 is 6. 6 divided by 2 is 3. Sure enough, looks like my graph wasn't too bad. So there's my center, -1, 3. So, what's that mean? This is going to be +1, right? It'll be x minus a -1. And this will be y minus 3, right? So there's my center, -1, 3. And now I need my radius. How do I get my radius? That's the distance formula, right? And I could call that r, I could call it d, whatever. But your distance formula, remember, which is just Pythagorean theorem, but you look at the distance formula, you just subtract your x's. So, and it doesn't matter what order, because you're going to square it. So 4 minus -6 squared. And then you're going to subtract your y's, -1 minus 7. I usually do them in the same order, but it doesn't really matter. So 4 minus -6 is 4 plus 6. That's 10 squared is 100. -1 minus 7 is -8 squared is 64. So So that distance is square root of 164. But is that the radius? That's the diameter. I think I might have said that we could call that R. Actually, we couldn't call that R, right? That's not the radius. That's a diameter. So what do we need? We need half that. Now, for right now, I'm okay if you just do this. Right? So 164 is not a nice number. And we could work with it and whatever you do. What's that? Oh, that would have been smarter. Yeah. We'll do that in a second. Let's finish this. Now, I'm not quite right here yet, though. What do I got? What am I missing here? So I just took half of this like that.
Oh, it's squared.
You got to square it. Remember, this is equals R squared. Probably one of the more common mistakes we will make is we'll either forget to square root that side to get the radius, or we'll forget to square. Now, when you square that, that just becomes 1/4 times 164, and that we can definitely simplify into 41. Okay? And we don't have time, the bells are ringing, but Noah had a good idea. Why not just do the distance formula between these two? Right? Just do the distance formula between those two, and that's your radius. Right there. Somebody mark that down. Noah had a good idea.
Don't.
Okay? All right. Just a couple things to finish up here, and then I'll let you work on some stuff here. In looking this over, after going through this, I wanted to show you another option, which for a lot of these problems would be the easier option probably. So we talked about when you have the number in front here, when you're completing the square, and actually on today's homework, now there's some IXLs, so that's a little longer term assignment. But there's some IXLs with the circles too, and there might be some completing the square in there. Today's book assignment doesn't take very long. Probably can get it done or come close today, because it's mostly about the standard form, and there isn't really any in the book of completing the square kind of stuff. And so on the IXLs or maybe, but definitely when we get to parabolas, we get to ellipses, those things, that's going to happen. The completing the square is going to happen more. So this idea of factoring out the 9, because you want to have a 1 in front of that x squared, that's important. But when you have an equation, when you have two sides like this, you can just divide everything by 9 also. Okay? Now, there will be potentially some times when you're dealing with functions, where we're dealing with these equations, where we want to do it as the factoring thing. And that's why I wanted to show that first, because when you factor out that 9 and you complete the square, you have to complete it inside of those parentheses. And then when you do your form, you got to keep the 9 with it. You got to keep the 9 with the other stuff. So I wanted to show you that. It ends up being here. Now, let me show you what it would look like if we just divide through both sides by 9. So if we take this same equation that we started with here, and we just divide everything by 9, it ends up being this. 12 divided by 9 is 4/3, 14/9, same thing, right? And then we take half of this. What's half of 4/3? 2/3, square it. And that's 2/3 squared, 4/9. And then we add 4/9 over here, right, to balance it out. And look what we get. We get x minus 2/3 squared on this side. And on this side, we get 18/9, which is 2. and we get to that same spot with a lot less mess than what happened through here, okay? So I just want to show you that, so probably most of the time with what we're going to be doing with the conics, we can do it this way, where we have the equation, we want to get a 1 in front of that square term, and so we can factor it out and do it the way we did, but it will be equivalent, it will work if we just divide by whatever's in front of that square and get that, okay? And then it works out the same, and it's a little less messy. Okay, so, but when we complete the square, we've got to have a 1 in front of this square. All right, so let's finish one more example. Yes, okay, right here. So let's go ahead and do that with the suggestion I just gave you, right? Notice there's a 2 in front of the x squared. There's also a 2 in front of the y squared. So that's nice. So what I want you to do is start this by dividing everything on both sides by 2. Start this by dividing everything by 2. But now let's get it into standard form. Complete the square, get it into standard form, write the center and the radius of the circle. Yeah.
Just a quick question, if you divide the 2 out completely, wouldn't you lose this solution? Or
No, because since what you're doing is you're dividing both sides by 2, which can't ever be 0. The problem when we lost a solution is if we divided by an x or something, where it potentially could be 0, we would lose a solution there.
Okay.
Yeah, as long as we divide by a constant, we're okay. Okay, so I've got a line up there to see if you got that far with me, or if you agree at that point. Okay, what numbers would go? What numbers did you have in here? 2.25 would be your decimal. Anybody do it as a fraction? Okay. I'm going to do this one as a fraction, and I'll show you the decimal one here. So it'd be 3, no, not 3. It'd be 9/4. So half of that is 3/2, and squared would be 9/4. But if you want to do 1.5 squared, 2.25 be fine. What about here? 4. Half of that is -2, square that is 4. So we'd have to add a 9/4 over here, we'd have to add a 4 over here. Got calculators, use decimals, use fractions, either one. If you get a messy decimal, a lot of decimal places of repeating, then you want to probably use fractions. Okay, so x plus 3/2, right? Whatever you got when you took half of this one is what goes in there, and you can test it by foiling it out. Same thing here, and we got to get those added over here, so that'd be -2 plus 2 1/4. -2 plus 2 1/4 would be 1/4. And then don't forget, then your radius is square root of that, which is 1/2. So your center, -3/2 and +2. Don't forget those signs end up being opposite. Okay, -3/2, 2. And then with decimals, it would look very similar. Like you said, this would be 2.25, this would be 4, 2.25, oops, that's not a 12. And then this would be a 4, okay? And so that would be, your numbers would look like that if you did decimals. Okay? All right. So, some book problems right here, and again, more long-term. Some ones that deal with circle on the IXLs. I think some of those are pretty quick and easy, identifying centers and stuff like that. This is clear back in chapter 1. So we're clear back on page 21, 22 for this, number 5, and then 69 through 82, which is just, again, identified. Most of them are in standard form. You don't have to do a bunch of what we've been doing with the completing the square. That may happen in the IXLs a little bit, but you know, trying to be working on those IXLs a little bit so you don't get yourself way behind. Plus, the practice would do you good now, not 2 weeks from now when we're done with circles and so forth. And that's not really the point, but okay. Did I stop there? Did I start the recording when we started?
Definitely not.
After lunch?